So in this lesson, we're going to look at finding probability and looking at different ways that games of chance can work and things like that. So we're just going to start off with some simple probability questions here. Number one is we're going to test some intuition about things, and all items are going to be considered fair for this point. We're not going to use like a special coin or a special deck of cards or anything that might give an unfair advantage to one side of the coin or the cards or whatever. So basically, how about tossing a head on one toss of a coin? Well, let's talk about this guy. We'll call him A. So for A, you've got a coin, and each coin has two sides. And with those two sides, only one of those is heads. So the probability that you would toss a coin and get heads is going to be 1 out of 2 choices. 1 out of 2. Part B, tossing 2 heads in a row on a toss of the coin. So let's just think about this for a second. If we've got this coin, and again it's fair, and we toss it twice, we could get heads and heads. We could get tails and tails. We could get heads, tails, and we could get tails, heads. And so we want to toss 2 heads in a row. So how many of these possible outcomes work? And if you're looking, there's only one. This guy right here. So there's 4 possible total outcomes, but there's only one of them that's going to work, so our probability would be 1 in 4. Alright, what about drawing a queen from a standard deck of 52 cards? Well, there's 1 queen. There are 52 total cards. So I'm thinking that the probability for this guy, actually there's 4 queens. There's 1 queen per suit. So there's going to be 4 queens. So the probability for this guy would be 4 choices, 4 possibilities out of 52 total cards. And you don't have to leave it as 4 out of 52. If you want to, you can go ahead and reduce that guy down to 1 over 13. Okay, what about rolling a sum of 4 on 2 dice? I wanted that to be hot pink. Let's call this D. Alright, so D. And you may remember we want to roll a sum of 4 on a single roll of the dice. So how can we get 4? If we roll 2 dice, how can we get 4? Well, we can get 4 by rolling a 2 and 2, by rolling a 1 and 3, by rolling a 3 and a 1, and then also again we could roll 2 and 2, but that would be the same. Okay, and so we've got 3 different ways that we can do this. Three ways to add up to 4. Now the question is, how many different ways can we add those dice together to get what we want? Well, you may remember from section 1, 9.1, when we were talking about counting, we can multiply those options together. So each die has 6 sides, so there's 6 times 6 different ways those dice can all work out. And so there's 36 total choices, total possibilities. I can't spell. Possibilities. And so then the odds, or not the odds, the probability of this guy then is going to be 3 out of 36 or 1 out of 12. The very last guy there, E, guessing all 6 numbers in the state lottery. Guessing all 6 numbers in the state lottery that requires you to pick 6 numbers between 1 and 46. Well, this is a combination, and so we did a whole sections on combinations and permutations. Combinations order is not important. So there's 46 total things to choose, and we're looking at combinations of 6 on those. And so if you look, there's only one way. Well, here's my total combinations. I'm going to go ahead and write this down. This is going to be 9,366,819 different ways to choose a lottery ticket. But remember, when you're playing a lottery, only one of those ways is going to win. There's only one winning number. So the probability of winning a lottery with 6 numbers, 6 picks between numbers 1 and 46 is 1 over 9,366,819. So here's how we can start looking at probability. And on our next slide, we're going to see a kind of a formula that will guide our thinking. Okay, so when you want to look at the probability of an event happening, what we could do is, if we're talking about outcomes that are equally likely, then we'll say that E is an event in a finite, in other words, there's only a limited number of choices, non-empty sample space, which means there has to be something in it, of equally likely outcomes. Think a 6-sided die, okay? Then the probability of the event E is the number of outcomes E that we want divided by the total number of outcomes in that sample space. So, like when we're talking about pulling a queen from a deck of cards, the event that we're interested in is the queen, and there are 4 of those. And the sample space is the deck of cards, and there are 52 of those. So that's where the probability, this is how the probability equation looks. And now let's look at some ways that we can use this. Alright, so we're looking at the sums from a pair of fair 6-sided dice. And for all of the problems that we're looking at today, we're going to talk about fair 6-sided dice. Find the probability of rolling a sum divisible by 3 on a single roll of 2 fair dice. And so when we look at this, we want a sum divisible by 3, so that automatically limits part of our outcomes. So we want things divided by 3, like 3 and 6 and 9 and 12. So if we're going to roll a die, then what we want to look at is the total number of outcomes we get from this that are divisible by 3, and there's 4 of those guys, okay? So we have to look at, then, with these 4, the probability that they could happen. So we're only interested in these 4 spots. And in order to get this probability of this event, what we'll do is we will add all the probabilities from these 4 events together. And when we do that, we'll get the probability of rolling 2 die and getting a number divisible by 3. So what are we looking at? Well, we're looking at 2 divided by 36 plus 5 divided by 36 plus 4 divided by 36 plus 12 divided by 36. And we're gonna add all these. Whoops, not 12 divided by 36. That should be 1 divided by 36. And so we're going to add all of these guys up, and whatever we get is going to be over 36 because we're dealing with fractions. So 2 and 5 is 7, 4 is 11, so we got 12 over 36. And 12 over 36 will reduce to 1/3. So there's a 1 in 3 chance that when we roll the dice, we'll get a sum divisible by 3. Okay, so if we have a probability function that we're given and we're told that this is, we're going to use this function to find probability, and that's going to assign a real number outcome to each sample space in our group S, then a couple of things have to happen. One, the probability has to be greater than 0 but less than or equal to 1 for every different possible outcome. And that the sum of all probabilities of all outcomes has to add up to 1. And that we can't have an empty set running through there. We can't have a 0. And so let's say we've got 1 over n. We got a 6-sided die, and we've got the probability function 1 over n squared plus 1. So if we've got a 6-sided die, then that means that we're looking at the numbers 1 through 6. 1, 2, 3, 4, 5, and 6. And we're going to just put these numbers in for n. So that here's our outcome on our die. And we're going to do our probability function. And we're going to get, so we would do each one of these. So we'd have 1 over 1 squared plus 1, which is going to be 1 over 2. And then 1 over 2 squared plus 1, which is going to be 1 over 5. Then 1 over 3 squared plus 1, which is going to be equal to 1 over 10. And then 1 over 4 squared plus 1. This is going to be equal to 1 over 17. 1 over 5 squared plus 1, which is going to be 1 over 26. And then 1 over 6 squared plus 1, which is going to be equal to 1 over 37. So the first thing that we need to look at is that all the probabilities are less than 0, or greater than 0 and less than 1. And they all are. The next thing then that we need to look at is, do we have an empty set? And no, we don't. And then the third thing is this middle guy right here, that the sum of the probabilities is 1. And so now you just have to add all these up on your calculator and get an answer. And if that answer is equal to 1, we're good. If the answer is not equal to 1, then this probability function is a false function. It won't work. So I'm just going to add these up real quick on my calculator. And I get 0.92. When I add all of these functions together, I add all of these functions together on my calculator. And when I do that, when I add them all up, I get 0.924. Since this is not equal to 1, this probability function will not work. Okay, so here's another question for you. Sal opens a box of a dozen chocolate creams and generously offers 2 of them to Val. Val likes vanilla creams the best, but all of the chocolates look alike on the outside. If 4 of the 12 are vanilla, what is the probability that both of Val's picks turn out to be vanilla? So basically we've got a total of 12 different objects. Okay, we've got 12 objects, and we're going to pull them out 2 at a time. Okay, and so we need to figure out all the different ways that we can do that. Well, that's a combination, so that's going to be 12 combinations taken 2 at a time. And when we look at that, that's 66 total outcomes. This is the first step of our problem, because remember, when you're determining probability, you have to determine how many total different things are in our sample. Well, there's 66 ways to pull out 2 vanillas in a row. Then we have to determine how many different ways that we can pull out the vanilla creams. Well, there's 4 of those. There's 4 vanilla creams. And we're taking those also 2 at a time. So now we're looking at 4 combinations of 2, which would be our success part of this. And so 4 combinations of 2 is 6. And this is picking 2. This is picking 2 vanilla creams. Okay. Well, in order to determine probability, I need the total number of things that I am looking for divided by my sample space. And so the probability that good old Val will get what he wants is 1 in 11. Okay, back to the same question that we just had with Sal and Val in that box of vanilla cream and chocolate creams. What we can do, there's a little bit of a different way that we can work it. We can look at the combinations like we did on the previous slide, or we can use this multiplication principle here. So suppose an event, that should be an event A has a probability P1, and event B has a probability P2, under the assumption that A occurs. Then the probability that both A and B occur is P1 times P2. So let's go back to that box of chocolate creams, and let's talk about what could happen. Basically, we've got 12 vanilla creams. All right. So the number in our sample space is going to be 12. Now, for Sal, there's when he chooses the thing that we're looking for, that we're interested in, we're looking for that vanilla, there's 4 ways that he can do that. So our first probability that we would look at in this case would be 4 over 12. There's 4 vanilla creams. There's 12 total vanilla creams. But wait, there's more. If you act now, you can also choose another vanilla cream from a sample of 11. And so we are going to go with the information that first time we drew out a vanilla cream, now we're going to say, hey, we've gotten one of these dozen items. There's only 11 left, but there's 3 vanilla creams left. So what's the probability then that we would choose a vanilla cream on the second one? And that would be 3 out of 11. And so if you multiply this guy straight across, you'll notice that you can do a little reducing, which is always very beneficial. So this becomes a 4, this becomes a 1. And you'll notice that your 4s divide out, and so I'm left with 1 out of 11. There's a 1 out of 11 chance that Val will get his vanilla cream. And this matches up exactly with the previous problem. So this is 2 different ways to solve one problem. This is called conditional probability, and it's similar to our chocolate cream question, but it depends on us pulling something out first. Okay, so the conditional probability formula. If the event B depends on A, in other words, we've got to pull out that first vanilla cream to get to the second vanilla cream, then what you're looking at is the probability of A and B divided by the probability of A. Okay, so 2 identical cookie jars are on a counter. Jar A contains 2 chocolate chip cookies and 2 peanut butter cookies. Jar B contains 1 chocolate chip cookie. Suppose we've drawn a cookie at random and it is chocolate chip. What is the probability that it came from jar A? So what we need to do then is we need to look at the probability that we pulled a cookie, chocolate chip cookie from jar A. And so when we do that, we're looking at the top part of my fraction here. So we're going to look up here, and we've got 2 chocolate chip cookies and 2 peanut butter cookies. Okay, so in order to pull 2 chocolate chip cookies, I've got a 2 in 4 chance of getting a chocolate chip cookie. All right, and out of those 2 cookies. The other thing is that I've got a 50-50 shot at getting all the way over to jar B. So that would be there's 2 jars and there's 4 cookies. So we're actually going to look at this in 2 pieces. A jar piece right here and then a cookie piece right here. So if I had like 4 jars, this would be a 1 out of 4. If I had 7 cookies, this would be 2 out of 7. Okay? So anyway, this is the top part of my fraction. And then divided by the probability that I could get a chocolate chip cookie. Well, how do I do that? How do I get that chocolate chip cookie? Well, I've got to look at all the different ways that I can get to the chocolate chip cookie. So there's there's basically three different probabilities that I can get a chocolate chip cookie. Okay, I've got the probability of getting into the correct, into the jars. All right. So, and then all the way into the chocolate chip cookie. So remember, once I go into a jar, if it's the A jar, I still have a 2 in 4 chance. So we kind of multiply all those things together. So I've got 2 jars. Okay. And so one of those jars, I'm going to have a chocolate chip cookie. And so I've got a 1 in 2 chance of getting it there. And then to get a chocolate chip cookie out, if I go into jar A, that would be 2 out of 4. But if I go into jar B, that would just be a half. Because if I go into jar B, I have a 1 in 2 shot of it's just picking the right jar. And then to get to that, actually, I'm going to change this just a little bit. There's 4 cookies, and if I pull 1 cookie out and it's chocolate chip, it's going to be 1 out of 4. And then I got a half a shot of getting into the right jar. And if I go back into jar A, I got another 1 in 4 shot of getting my chocolate chip cookie. So this is my setup on this guy, and it looks kind of confusing, but this is how it would go. A visual for this would be something like, if I start here and I go to jar A and I go to jar B. Okay, think about it this way. I got a 1 in 2 probability of going to jar A or B. I mean, I've got 2 choices. One of those is going to be correct. Once I get into jar A, though, there's 4 options that I've got. And once I go into jar B, there's 1 option that I've got. And this is going to go right to my chocolate chip cookie. So there's my 1/2. Here's my 1/2 times 1 right here. But then to get to the chocolate chip cookie with A, I've got a chocolate chip cookie here, a chocolate chip cookie here, a peanut butter cookie here, and a peanut butter cookie here. So what are the odds that I can pull out a chocolate chip cookie? Well, I've got a 1 in 4 shot with this guy and with this guy. I've also got a 1 in 4 shot of getting peanut butter for both the peanut butters. And so what I'm looking at then for this particular one is my 1/4 times 1/2. That's that guy. And my 1/4 times 1/2. That's that guy. So that's how this problem then will set up. And so you're going to end up with 2 over 8 over 1/8 plus a half plus an eighth. And so when you reduce all of that down, you're going to end up with, there's a 1 in 3 shot of getting a chocolate chip cookie from jar A. Okay, so let's look at rolling a fair die again 4 times. Find the probability that we will roll all 3s. And so if we're just rolling a single die and there are 6 sides on that die, then what we're looking at is there's one way to roll a 3. And then if we do that 4 times, okay, then we're looking at that multiplication principle, which is just going to be 1 over 6 to the 4th power, which would be 1 over, and then 6 to the 4th. 1 over 1296. So if you wanted to write that as a decimal, you can just divide it out, not a problem. Okay. What about number 2? We want to roll no 3s at all. No 3s at all. Well, how many different ways can we do that? 5. And so there's 5 ways. There's 6 sides on the die. So we're looking at this guy, and also we're rolling it 4 times. And since we're rolling it 4 times, then we're again looking at the multiplication principle. And this time we would do 5 over 6 to the fourth. And 5 to the fourth is 625. So we would have 625 over 1296. Okay? And if you wanted to, you could reduce that, you know, all the way down. Now, what about rolling exactly 2 3s? Okay, if we want to roll exactly 2 3s, well, the probability of rolling 2 3s would be, you know, 1 over 6. That's the first guy, and we want to do this twice. Okay, so it'd be squared. And we're rolling it 4 times, so we would have 2 3s times, and then the other 2 rolls would not be 3s, so that's 5 over 6. Okay? And that's going to give us 25 over 1296. Okay? But then we have to also consider that there are other places maybe that those 2 3s could show up. Like, you know, this is showing up if we roll 2 3s first and then we roll 2 non-3s. Well, what if out of those 4 die rolls, what if we rolled a 3 somewhere else, or at the beginning, or in the middle, or at the end? So now we're looking at combinations. Okay? So the combination part of this then is going to look at, there's 4 different ways, or there's 4 different spaces to fill. Let's see. There's 4 different spaces to fill. There's 2 specific answers that we're seeking. So we're looking at a combination of 4 things taken 2 at a time, and there's 6 ways to do that. So this is 6 total outcomes. Whoa, 6 total outcomes. Okay, there's 6 total outcomes, but we've also got to consider all the possible ways that are out there for us to do this, and that is from this guy right here. So what we would do is we would just take that 4 combinations of 2 or 6, and we would just go 6 times the rolling the exactly 2 3s part, which is going to be 25 over 1296. So 6 times 25. So this is going to be 150 over 1296. And if you wanted to decimal this out, you could punch that in as well. So, you know, on that last one, exactly 2 3s, there's a little bit more work that's involved because we have to look at all the different ways that we can do it, and then the specific combinations of those ways. Alright, so let's look at binomial distribution now. And suppose we've got some sort of experiment that has independent repetitions with only 2 outcomes, like a heads or tails on a coin, or like making a free throw or missing a free throw. You know, some sort of just success or just failure. So when you look at the binomial expansion, which was in your previous section, the terms of the binomial expansion give the respective probability of success. So repetitions is not spelled correctly, but the number of successes out of n independent repetitions. So this should be repetitions. And then the probability of that. And so we're going to look at a problem on the next slide that kind of uses this setup right here. So, you know, if you've got n repetitions, then the probability is p to the n. Okay, if you've got n minus 1 repetition, so in other words, not 1 less, then you've got n over n minus 1 combinations times p to the n minus 1 times q. And so the q would be the failure. Okay, so if you shoot 20 free throws and you make 19, then the number of successes would be 19, and then your number of failures, which would be the q part, would be 1. And that's what our next example is going to look like. Suppose that Michael makes 90% of his free throws. If he shoots 20, and his chances of making each one is independent of the others, an assumption you might question in a game situation. What are the probability that he makes all 20? And so, going back to the previous slide, okay, if you pause and rewind and look at that previous slide, then our n value is our number of successes. And so n in this case is 20. And the Q then is just there are no failures. So we're looking at that very top row on that chart, which means that then I've got my my p-value, okay, which is 90%, okay, 20 successes. So here's my 90% part. So what I'm going to have is the probability of it happening, 0.9 to the 20th power. Okay, and that is roughly, I'll take it out 4 decimal places just so we can see, 0.1216. So if we go with the fact that Michael makes 90% of his free throws, the probability of him hitting all 20 is 0.1216. Well, what if he's got exactly 18 successes? So now we're looking at where our n value is 20, okay, but we've got 2 failures in there. So what I end up with then is going to be 20 total free throws, okay. So now I'm looking at the middle of that chart. 20 combinations of 18, and then times my p-value. So that's going to be 0.9 because I shoot 90%. And of those 90%, I made 18. And then there's a 10% chance I'll miss, and I missed 2. So we would punch all of that into your calculator. And so when you do that, you get 20 choose 18 times 0.9 to the 18th power times 0.1 squared. And when I do this, and I'm going to carry it out 4 decimal places, I get 0.2852. Okay. Well, what if he makes at least 18? So he could make 19, he could make 20, but he makes at least 18. So what we have to look for that on question 3 then is we're looking for 3 different ones. We're looking for the probability that he gets 18, plus the probability that he gets 19, plus the probability that he makes all 20. Okay, so we're looking at all 3 of these instances. Well, we've done 2 of those. We've done 18 and we've done 20. So 18 is going to be 0.2852. Okay, we've done 20, which is 0.1216. So for 19, so if n is going to be 20 minus 1, that would be 19. Then we're looking at 20 choose 19, 20 combinations of 19, times 0.9, my 90%. And how many times did we make 90%? 19 times. And then how many times did we miss? 1 time. And so this is your setup for that guy. And when you punch him in, you get 20 choose 19 times 0.9 to the 19th times 0.1. 0.2702. So we would take this guy right here, and this is my 19 part. So I'm just going to add these guys up, and when I add these guys up, that's going to give me my probability of making at least 18. So I'm going to punch that in right now. and I get 0.677 of at least 18.